All right, here are some selected questions from chapter 15. So the first one, for a second order reaction, the initial reactant concentration A0 is 0.91. After 11.1 seconds, the concentration is 0.51. What is A after 51 seconds? All right, so it's a second order reaction. They tell you that right off the bat. This is very important, helpful information. What we know from that is that the second order integrated rate law is 1 over A equals KT plus 1 over A0. This means the graph between 1 over A and T is a straight line with the slope being the rate constant K. But that information is not too important right now. But what we can use from the equation is we can plug in values. So when A0 is 0.91, we can put that into A0. After 11.1 seconds, it's 0.51. So what we can do is we can plug in our time and our new A concentration to solve for K. Then we can use our newfound K, since K is the same for every reaction condition. It doesn't change. What we can do then is put in 51 seconds and determine our new concentration of A after 51 seconds. So let's do the first step. We're going to put in 1 over 0.51 equals K times 11.1 seconds plus 1 over our A0, 0.91. And keep in mind, A0 is always the same for a specific case reaction because that's the initial concentration of the reactant. So what we can do is solve for K, and that would be 1 over 0.51 minus 1 over 0.91, that in parentheses, divided by 11.1. And that would equal 0.0776. And that would be K. Since it is a second order rate law, the units for K are going to be 1 over molar times 1 over seconds. So now we want to figure out what is the concentration of A after 51 seconds. So we can plug in another second order rate law, integrated rate law. So it'd be 1 over A, since that's what we're trying to find in this case, equals KT. Now our K, we know already, is 0.0776. Our T, meaning our time that we're trying to find the concentration of A at, is 51, plus 1 over A0, which again is 0.91. So we can use this information to solve for A. So we can multiply A to the right side and divide by everything else. So the answer would be 1 over the entire right side of the equation, 0.0776 times 51 plus 1 over 0.91, which equals 0.19 molar. Now, does this make sense? Our initial concentration of A is 0.91. After 11 seconds, it's 0.51. After 51 seconds, we should think, all right, it must be a lot less than that. So that's true. We got 0.198, which is a lot less than 0.51 and a lot less than 0.91. So that makes sense, especially for a second order rate law. Moving on to the second one. For a reaction, D yields A plus C. When 1 over D is plotted versus time, it gives a straight line whose slope is 0.028 per molar per second. What is the concentration of D after 39 seconds if D0 equals 0.8? Now, this is another second order rate law. And we know that because 1 over the concentration of D plotted versus time is a straight line. So again, the integrated rate law for second order is 1 over A equals KT plus 1 over A0. Now it's asking for, it gives us the slope. So the slope is 0.028. The slope is the same thing as the rate constant. So we know K already. What is the concentration of D after 39 seconds? So we know T. If D0 is 0.8, and that's A0. So we can simply just plug in everything to figure out our value for D. And we're going to use D instead of A this time since the question refers to it as D. So we have 1 over D. equals our K, which is 0.028, times our time, which is 39 seconds, plus 1 over D0, which is 0.8. And we can solve this very similarly to how we solved the previous one. Multiply both sides by D and divide both sides by this entire right side of the equation. So we have 1 over 0.028 times 39 plus 1 over 0.8. And that's going to equal 0.427 molar. Now, does this make sense? Our initial concentration is 0.8. After 39 seconds, it should be less. And yep, it's less. So that makes sense. All right, next question. Evaluate each of the following proposed mechanisms to determine whether it is consistent with the experimental results and identify intermediates, if any. So what we're trying to do basically is figure out what X and Y are in this reaction rate. Now, and we've given our elementary steps. Now, what we know is that the slowest intermediate elementary step represents the rate of the overall reaction, which the rate of the overall reaction is given right here as K times NO2 concentration times O3 concentration, since this is the overall reaction. Now, keep in mind, this rate law is found experimentally. So it's not, for the intermediates, you can determine their molecularity, but for the overall reaction, you can't determine its molecularity. It has to be determined experimentally. That's why this isn't rate equals K times NO2 squared, like this reaction would suggest if it were an elementary reaction. But in this case, we can't do that. But for the elementary reactions, these two, A and B, the fast and the slow, we can use these values to figure out its molecularity and their rate laws. So what we can do is for the fast one, we can say that NO2 squared times K1 equals the rate of the fast one. And we could say the same equal rate is going to be the backwards reaction, which is K minus 1 times N2O4 equals the rate for the fast. And that's the same. So these should be, since the forward needs to equal the reverse at equilibrium, we can say that these are going to be equal rates. So we'll do K1 times NO2 squared equals K minus 1 times N2O4. All right, now our slow reaction. Our slow reaction, we can determine the molecularity as in the forward direction. We can call this K2. We can say that the rate overall, so rate, I'll put rate overall, equals K2 times N2O4 times O3. So now our goal right now is to figure out how does the rate of overall reaction determined by the slow reaction equal this rate of the overall reaction completely. That's experimentally determined. So the only thing that's different between these, we have O3 is the same. The only thing that's different is you want to get this N2O4 in terms of NO2. And we can do that. So we can solve for N2O4 using our fast rate right here, which is what we just figured out. So let's solve for N2O4. You're going to have K1 divided by K minus 1 equals NO2 squared. This is going to equal N2O4. And we can plug in this N2O4 to our rate of our overall reaction determined by the slowest elementary step. And let's take that over here and see if they equal the experimental rate. So our rate would equal K2 times the N2O4. Now N2O4 is now K1 over K minus 1 times NO2 squared. Now we have O3. Now from this data, we see that the rates are different. This means that the rate of our proposed mechanism which is the rate that's experimental rate, is not the same as the rate we calculate in theoretical. So it's not consistent. So this doesn't work. Now we can still figure out the x and y values for the rate law. And all these k's can condense. So our final proposed rate, our calculated rate law, is k times NO2 squared times O3. Now we know our value for x is going to be 2. So x equals 2 and y is going to equal 1. And with any experimental data, you can determine the rate of this reaction. Next one, determine the rate constant from the concentration time dependence. And the units for the initial rate are molar per second. All right, so we want to see, based on this experimental data, what a change in A and a change in B does to the rate. So in our, we'll call these trials 1, 2, and 3. In trial 1, we have certain values. In trial 2, when we compare the two, B is held constant and A almost doubles. Let's look at what happens to the initial rate. The initial rate almost doubles. So the fact that A multiplies by, let's say it's 1.8, and the initial rate of the reaction multiplies by 1.8 when B is held constant, this means that A is a first order reactant. So we'll put, if this was the rate law, K times A to the X times B to the Y equals the rate, we can say that X is equal to 1. Meaning A is in the first order. Now for B, let's try to figure that out. In some of these questions, this is a tougher version because you don't have A being held constant anywhere. But what you can do, for example, now we're going to be comparing trials 2 and 3. A is not held constant and neither is B. But we know the initial rate, how it should behave when A is multiplied. So let's try to figure that out first. Ignore these initial rates for now. We'll talk about 0.096. That's initial rate. Now, when, let's say B was held constant. When A goes from 0.035 to 0.50, that change, if we divide the two values, is 1.42 times. If that's the case, then the initial rate should change by 1.42 times. So the initial rate, if B was held constant, would be 0.137 if B was constant. But it's not. B changes by more than twice the amount. So we want to figure out what is the difference in multiplicity between this 0.137 and the 0.75 in trial 3. That difference will give us the amount of rate of reaction that is responsible or that corresponds to the change in B. So 0.35 divided by 0.15. We want to see the difference in multiplicity. And that difference is 2.33. All right. So if B was in first order and A was in first order, that means if they both double, the initial rate should quadruple because it doubles for each one. But B in this case, so let's say A doubled or A multiplied by 1.42, that corresponded to the rate increase of 1.42 times the rate 0.096. The remaining rate increase to go to 0.75 is due to B. So when B changed by multiplied by 2.33, what did the rate do? So the rate actually increased by 0.75 divided by 0.137. This is just corresponding to B now. And dividing those values, you get 5.47. So in the concentration doubling, or a little bit more than doubling, the initial rate multiplied by about 5.5. So this definitely isn't first order in B, but is it second order? So if we square the 2.33, we end up with 5.42. That is very close to the 5.47, which means that when A doubles, the rate will double. But when B doubles, the rate will quadruple. So having both of those mechanisms at the same time means that when A increases by a certain amount, the same certain amount is increased of the rate. But when B increases by a certain amount, that certain amount has to be squared and added on to the initial rate, accounting for this large rate increase. So we can say that y, meaning the coefficient of b, or sorry, the exponent for b, is in a second order. So our rate law, or we're determining our rate constant too. So our rate law is going to be k times a to the 1 times b to the 2 equals the rate. Now, that's the tough part. The easy part is now determining the constant. So we have k, which is unknown, times a. We could just pick, let's say, trial 1. We have 0.02 times b squared, which in trial 1 is 0.15 squared equals the rate for trial 1, 0.055. And we can do some math and figure out the rate constant, which is 122. Next question. Consider the second order decomposition. At 450 degrees, the rate constant is 15.4 atm per second. Now, it's not molar per second. In this case, atm per second, we're dealing with gases. How much time is needed for NaCl, originally at pressure of 86 torr, to decay to 90 or 19.2 torr? Now, it's a second order decomposition. So what we can say is that 1 over, in this case, the pressure of A equals kT plus 1 over the pressure A0, meaning the initial pressure. So let's plug in some values. The rate constant, or we can say we're looking for the time. So we would have 1 over the partial pressure of A in the final stage, which is 19.2 torr. So we can just do 19.2 divided by 760 to convert to ATM, equals K, which is given as 15.4 ATM per second. And we're looking for time, plus A0, in this case, would be its original partial pressure of 86. So 86 divided by 760. Now we can solve for that. Now, for the next part, how much time in seconds is needed for NaCl, originally at a concentration of 0.0131 to decay to 0.022? Same exact approach, but we have something different here. We have concentration, not pressure. So this rate constant is at 15.4 per ATM per second. This can't be used. The ATM has to be converted to molarity per second in order to have the same variables. Now we can do that. If we bring back one of our handy-dandy ideal gas law equations, PV equals nRT, we have the temperature of this reaction. And if you manipulate this expression, you get the pressure times, or sorry, the pressure divided by RT equals N over V. Now, what is N over V? N over V is moles divided by liters. That's exactly what we need. We need molarity. So what we can do is do P over RT, which would be 15.4 divided by 0.0806 times our temperature, which is 450 Kelvin, 0.417. So that's going to be our new rate constant. It's 0.417 molar per second. So now we can do the same exact thing we did. We could do 1 over the concentration of, or final concentration of A, which it would decay to 0.0022 equals our new rate constant, 0.417 times T, plus 1 over our initial rate, which is our initial concentration, sorry, 0.0131, and we can solve for T. And T is a large value, 907 seconds. So that takes a while. But that's how you do that. So make sure your units are the same, and this is a pretty tough question. That's why we're going over it. But just keep that in mind. Next one has to do with energy. So a catalyst decreases the activation energy of a particular exothermic reaction by 54 kilojoules to 67 kilojoules. And it's exothermic. Keep that in mind. Assuming that the mechanism only has one step, and that the products are 99 kilojoules lower in energy than the reactants, sketch an approximate energy level diagram for the catalyzed and uncatalyzed reaction. Then answer, what is the activation energy of the uncatalyzed reverse reaction? Okay, so I see sketch an energy level diagram, and it's exothermic. So let's do that. We have energy versus time. And this is the reactants, so I'll put R, and it's exothermic, meaning it's going to go like that. And you have products on the bottom. This is our midpoint, our middle line. Sorry, it's wavy, but whatever. All right, so it says it decreases, the catalyst decreases it by 54 to 67. So we can say that with the catalyst, which we'll call at this point, this is now 67. Without the catalyst, it's 67 plus 54. So we can say this distance is 54. Because what the catalyst does, it decreases it by 54 to now make it 67. And also we're given the information that the products are 99 kilojoules lower than the reactants. So we can say the distance between the reactant energy and the final products is 99 kilojoules. So what is the activation energy for the uncatalyzed reverse reaction? For the catalyzed reverse react, or for the uncatalyzed forward reaction, meaning starting from the reactants, we're going up the hill, and it's going to be 54 plus 67. For the reverse reaction, since it's going from products to reactants, we have a larger hill to climb. It's an endothermic reaction, and we have to go all the way down here to all the way up here. And that distance is the 99 plus the 67 plus the 54, which would equal 220. So the total distance between the products and the amount of energy needed to go from products to reactants is 220 kilojoules. So that is how that would work. And you can figure out a lot from this graph. You can figure out the catalyzed reverse reaction, which would just be 220 minus 54. You could figure out the catalyzed forward reaction, which is 67. You can figure out the catalyzed or the uncatalyzed forward reaction, which is 54 plus 67, and a lot of other things as well.